we still have a little bit of time to start talking about relativity, special relativity. Maybe you can briefly say how much have you already done? I mean, I guess modern physics class, so when it was, how far did you get there? What did you, anybody summarize what you covered? Not much left over. Okay, maybe we start with just the main starting points that look pretty innocent, but pretty much everything from relativity comes out of those two postulates. Right? Who can tell me what's the two postulates of relativity? So what are the main postulates, the main statements from which essentially everything starts out?
The speed of light in a vacuum is always constant, and that the laws of physics hold for the exact same for every inertial system.
Exactly. Those are the 2 points. So the first is essentially the postulate of relativity, right? That means so physics is the same in all. Same in all inertial frames. What is that? First of all, what do I mean by inertial frame? What is that?
Non-accelerating.
Exactly. Non-accelerating frame, can it be moving or does it have to be stationary? Exactly. So from that, also, so there's several other ways to phrase that as well. So that means you make an experiment in any frame, it can be moving with any arbitrary speed with respect to me or you or anything else. That also means you cannot actually make an experiment that tells you how fast you are moving. So you can always define yourself as the thing that's not moving and everything else is moving. There's no concept of absolute motion or absolute velocity. That's why it's called relativity. All motion can only be defined relatively. There's no such thing as absolute motion. And the second, that is actually slightly counterintuitive, right? So that means speed of light, vacuum, right, is always c. Most important here is irrespective of relative motion, right? Motion between source and that already at the beginning of class today, right, when we talked about this light travel time difference, where it says the source might move with a certain speed almost towards us, and the light reaches us still only with the speed of light. Where intuitively, of course, you would think if you're already moving fast towards the source and then you shoot out a light ray, you would expect the light ray is actually faster. So this fundamental, so to say, speed limit of the universe, that is in fact from which everything can now be derived, time contraction, time dilation, length contractions, and so on. It's all a fact of this. Does anybody know? And it's not something that you would intuitively expect, right? And up until 19th century, end of 19th century, people were actually thinking that there might be something, some kind of ether or so that carries light waves, and if you move relative to that, obviously you would see a different speed of light. Does anybody know what experiment it was that actually disproved that?
Michelson-Morley.
Michelson-Morley, yeah. Can you explain what that is or what that did?
Interferometers.
Yeah.
Then, it was as the Earth moved, I think through the ether, they were supposed to measure the contraction. One of the as the laser is, I think you'll have a interference, but then they didn't pick up anything. So there wasn't anything.
That's not exactly right. So you had essentially coherent light that was split up into two beams and brought back into interference, right? And that way you can measure if they're equally long, you have positive interference, you see essentially a bright spot here, right? But if, say, the speed along one of the directions changes a little bit, then you can change from positive to negative interference here, so you will measure that, right? And so, exactly as this is of course sitting on Earth, and Earth, say, is moving in that direction, you would expect that this kind of has to go against the ether flow, as this goes perpendicular to the ether flow, and you would have different average speeds. And the result was nothing. So that is really the point that, or the experiment that proved that in fact the speed of light does not depend on relative motion between source and receiver. And that, as I said, this really is the starting point of all of relativity. Now what we're doing from now is simply develop the framework of special relativity for mechanics. But then, of course, since this is electrodynamics, we'll then see how this all fits in with electrodynamics as well. Nice thing with electrodynamics is that it's a theory that is inherently already built in, or has relativity already inherently built in. And you can probably guess that already from this identity, from this fundamental constants, right? That mu naught epsilon naught was. Squared, right? So this is already kind of a sign that this constancy of speed of light is already kind of built into electrodynamics. And at the very end of the class, I'll actually write pretty much all of electrodynamics in one little nice coherent formula, which is actually quite useless, but it's a nice thing to have this complete coherent picture now, essentially all coming together. But there are a little bit of work to do to get there. So you've probably heard about some of the consequences that this now has, like the time dilation, length contraction, and so. But I guess in the previous class we haven't really derived how this actually comes about from this fundamental principle. So let me start out with some thought experiment. So let's say I have just a railroad car. So that has some length, some height h. I have a light bulb up here, and send a ray of light down this height h, and see. So this is 0 at time t reaches. And now, if we're sitting in the car, let's call this t prime. We're in the car sending the ray right down. And then, of course, we know that this moves with the speed of light. So h is c t prime, or we have time t prime is just h over c. Okay, now let's do something else and look at the same experiment, but the car is now driving with some velocity v. And now we're standing outside. Still, the light ray comes down straight. It's the same point. But after this time v, well, the bottom point has actually moved a little bit, right? So it has actually moved the time e delta t. And it has actually traveled more. But now, so the height, we're moving in that direction. Let's say that doesn't change. Delta t. Now this is, it's still moving with the speed of light c. Okay. So the length here is now, this is still h. So h squared plus e delta t squared. Square root is now c delta t, right? So now a stationary frame in which the car is moving. The light ray has actually passed this time. So now say h is the same, the speed of light is always the same. So let's say h is c t prime. So let's put in h here, right? So this is square root of c, actually it's delta, let's just call it t. So c squared t prime squared plus b squared t squared is c times t. Okay. So can we resolve this now for t prime? So c squared t squared is t prime squared is then c squared t squared minus b squared t squared, or c squared t squared 1 minus c squared, right? And now remember, this is 1 minus beta squared, that is 1 over gamma squared. That is our Lorentz factor. And that's how you see how this actually comes in. So we see that the time in the car, co-moving in the car, so since the speed of light is the same, this height is the same, the only thing that must be different then must be the times. So the time in the car is the time in the stationary frame divided by m. So that means that's of course the effect of time dilation. So that means in a moving frame relative to v, time passes more slowly, less time passes in the fast moving. That of course brings us to a whole lot of paradoxes that we have to learn how to resolve. Because, well, if we now say we're stationary, the car moves, less time passes in the car, why can't somebody sitting in the car saying, no, the ground moves, there should be less time passing in the ground? In principle, yes. So that's the fundamental problem of actually how can those two compare what time it is. In order to compare what time it is, you kind of have to either send signals that take time or come back together. And again, if you move it and come back together, somehow, well, suddenly you're turning around, you're accelerating, you're no longer in a stationary frame, in an inertial. So we'll learn in the next couple of weeks how, actually probably already next week, how you actually resolve these kind of paradoxes. That you seem to both see the other clock going more slowly. But in principle, both are actually right. The fundamental issue here is saying, so if you compare times, you have to have some kind of agreement what happens at the same time. So now, so there's a nice illustration here as well. So again, let's put ourselves in some car. It's moving with some speed v. And in the middle, we have a light bulb here. So light bulb, let's say that's exactly in the middle. And that sends light pulses back here and back there. So let's say if these are the same distances, that means there's a time at which it hits the back of the car, and there's a time at which it hits the front of the car. And let's say we look at that in the frame of this car, so it's all primed against the moving frame. Then, if that's exactly in the middle, obviously TA will be the same, right? So it will hit the front and the back of the car at the same time. But now, what happens to somebody with stationary here and actually sees this moving with velocity? Then, by the time this light ray hits the back, the car is actually, let's say, already here, right? So it has already moved some kind of E times TA. But that means it hits it already at a much earlier time. Whereas the front end of the car has moved some VTB here. That means it has to go way further, right? So while in the one frame, hitting the front and the back end happen at the same time, suddenly in the stationary frame, we'll notice that TB actually happens much later than TA. So that is a fundamental thing that ultimately will help us resolve all of these paradoxes with measuring different times, is that also the simultaneity is relative. So the relativity of simultaneity. So from now on, we'll have to be very careful when we are saying two things happen at a certain time or two things happen at the same time. We always have to be aware that that is true in one frame. Any other frame moving relative to it will actually not see that at the same time. So what happens at the same time not depends on whether you're moving. All right. Does that all make sense so far? That's the thing about relativity. It's kind of logical, but if you try to imagine things, it's kind of starting to blow your mind a little bit. Because it's really quite far away from your everyday experience where everything is very slow compared to the speed a lot. And next week, actually, we'll start with a little movie, a very nice movie that illustrates all of these different effects of special relativity in a nice way. So that will actually going to help you a little bit wrap your head around all these actual effects. Okay, shall we do one more experiment here and say now, again, we have our car in one stationary frame that moves with some velocity v. And we do a similar experiment, now saying, so this is this car in total length L, and we're sending a light ray, say, to a mirror here, and let it light. Of course, the light ray travels with the speed of light, and let's call this L prime, as that is the length that we measure when we are sitting in the car. So you see I'm getting into length contraction now. Okay, and we know that L prime is C delta T prime, right? Or this is actually going one way, going back, just have two of those, right? Okay, now let's look at some other frame where we're stationary and the car is actually moving. Then, by the time we hit the end, the car has actually moved some extra distance, v delta t, right? So that means that distance we're actually traveling this, essentially this, well, this is L prime plus E delta t. Exactly, so that's essentially the length that we see here is then L prime plus the V delta t. So C times delta t, the total distance traveled here, is then actually this L prime plus delta t, right? So it has a little bit longer delta t1. That's the distance to going there. Going back, actually, from here, the car has traveled another length v delta t. So c delta t2 will be prime minus v delta t. Right? Okay, so now we can say that our time delta t prime is our L prime over 2c, and our time delta t, if you solve that, just add the two up. And so just write, so delta t1 c minus v equals L prime, right? And t2 is plus L prime, right? So the total delta t, add the two up, is, so is sum of the two is L prime 1 over c minus e plus 1 over c plus e, right? Equals, this is now so L prime c plus v, so over c squared minus v squared, c plus v plus c minus v, right? So is this 2L prime c over c squared minus v squared, or 2L prime over c minus v squared over c squared, and that is 1 over minus squared. So it's 2L prime over c times squared. But now we have t this twice the distance. Alright, so now what we have is delta t prime is 2L prime over c, whereas sorry, I'm messing things up here. The length L, of course, are the length measured in the stationary frame. It's not the same length. I didn't expect it to look like this fast. Prepare very. Okay, good. So that means, but we know from the time contraction that delta t prime is delta t over gamma, right? So that is, that's 2L prime over c, but that is also delta t over gamma is 2L gamma over c. So that means L prime is gamma times L. So that means if we are in the stationary frame and we see something moving with some speed that corresponds to the Lorentz vector gamma, we actually see it contracted by L. So that means if we see the car moving at a certain speed, we see its length contracted by some Lorentz vector gamma. So this is called Lorentz contraction. Sorry for the confusion here a little bit. Did it become clear so far? So all we've done is just calculating the times it takes to go back and forth, taking into account the motion in the stationary frame, and then we had already calculated the time relation, so we can account for that. And then we figure out that moving objects apparently seem short. Which again gives you a paradox, right? Because somebody in the car might say, I'm stationary, so I see some length on the ground there, that's moving with respect to me, that is actually short. So who's right? So we'll discuss this much more. This leads us to one famous paradox called this ladder and barn paradox. They play around with exactly that every observer would seem to see the other one contracted. And so you can't really fit the ladder and the barn in one frame and find which the other frame is. But we'll discuss that in much more detail next time. Any questions on this? If not, then see you all next week.